So let's begin today's lecture, which is a continuation of our discussion of graphical models, Bayes nets. And just to remind us all, here's what we mean by a Bayes net. It's just a notation for describing a joint probability distribution over a collection of random variables. That's all it is, really, a notation. Very convenient one. And so how does that notation work? Well, a Bayes net represents that joint probability distribution according to this formula. So if we have a collection of random variables, x1 through xn, what the Bayes net tells us is how we can more simply represent that joint distribution compared to our default approach of building a huge table with all the possible configurations of values for x1 through xn, which even if those were Boolean variables, of course, we'd have 2 to the n rows in that table. What the Bayes net tells us is that instead of that tedious, complete, complex 2 to the n representation of the joint distribution, we can represent it instead as the product of some simpler distributions. And that corresponds, as we know, to making a bunch of conditional independence assumptions. And so being able to represent these joint distributions more simply actually pays off in two very different ways. One is whenever we need to do some inference, if somebody gives us a Bayes net of x sub 7 being 1, given that x sub 5 and x sub 3 are 0, so if they give us that kind of an inference questions, then of course we could solve it with the exhaustive table representation of the joint distribution. We just have to sum up all the rows in the table for which the denominator would be true and sum up all the rows where the denominator plus the numerator would be, well, you know what I mean, where all three of those variables would have their assigned values. Look at the ratio. We could always do that as kind of our default strategy. But if we can represent it more simply, then often we can compute those kinds of, the answers to those kinds of inference questions with less complexity. Not always. It turns out, unfortunately, inference in Bayes nets is also NP hard in general, in the worst case. But for some kinds of Bayes nets, as we'll see today, we can actually do inference in a lot less than 2 to the n complexity. Okay, so that's one way it pays off. But it also pays off more obviously to us in this course when we go to learn a Bayes net. And that's because, well, the same reason that naive Bayes is easier to learn. What do I mean by easier to learn? Naive Bayes requires fewer training examples to get reliable estimates of the joint distribution of y and all the x sub i's. Naive Bayes requires fewer training examples to get reliable estimates of those parameters than a Bayesian classifier that represents the joint distribution this way. And so the second way that Bayes nets bias something is by virtue of having these implicit conditional independence assumptions, they reduce what we call the sample complexity, the number of training examples that we need to see to reliably estimate the parameters of the model. Okay, so that's kind of where we were with Bayes nets. Today I want to look at a couple issues. One is inference. We'll spend a little bit of time on that, and then I want to come back to the question of exactly what conditional independence assumptions are implied by a Bayes net. We'll take a more detailed look at that and a more complete look than we did last time. Okay, so the story on inference is kind of sad, to be honest. I wish I could stand here and tell you Bayes nets make probabilistic inference easy, but they don't. It's still NP hard in the worst case. And as I mentioned, in some cases, it's tractable. if you look at the published papers on graphical models in Bayes nets, it's kind of disappointing, but I would say, by my assessment, there's more text pages devoted to how could we do the inference in this Bayes net than there is devoted to how do we learn these things. So inference in Bayes nets is actually a big hassle if you have an arbitrary Bayes net. It just follows from the fact that inference is NP complete. But there are a bunch of methods, and we're not in this course going to get into their details because that's not really the main thrust of our class here. But as I mentioned last time, if you're interested in this area, there's an entire semester-long course on graphical models that you're welcome to take. Once you have this course, you'll have the prerequisites that you need to take that. And that semester-long course goes into a lot more detail on the question of how to do inference tractably. And we'll kind of sample some of the ideas today. Okay, so let's start with this simple Bayes net, which we looked at last time, which essentially tells us that we have 5, in this case I'm going to assume they're Boolean variables. See, whenever I describe a Bayes net, the things I describe are what's the graph structure, and then I tell you for each node in the graph, what kind of a Boolean, or what kind of a random variable is this? What kind of values can it take on? Is it real valued? Is it Boolean valued? And then the third thing I tell you, of course, are the conditional probability tables for each of those nodes in the graph, conditioned on their immediate parents. Once I've told you those things, then you know everything about the Bayes net. So in this case, I'm going to assume these are Boolean variables. We have these 5, and that's the structure of the Bayes net. I haven't yet told you what the specific conditional probability tables are for each of these nodes, but that's okay. Let's just look at the inference problem starting with this Bayes net. Okay, so again, I'm assuming these are Boolean valued variables. And in general, one kind of obvious question to ask in terms of inference is, how do we use a Bayes net like this to figure out the probability of a particular specific assignment to every one of the variables? And in general, I'm going to use uppercase to refer to variable names, and I'll use lowercase to refer to their values. And I'll follow this notation. It's fairly common. Not everybody uses it, but a lot of people in the research literature use the same notation. And I'll even use this kind of shorthand notation a lot. If I don't want to actually write out in detail the variable uppercase A has the value lowercase a, I'll just kind of abbreviate it this way. Okay, so given that I do have the conditional probability tables for each one of these nodes, I'll just assume I have a little table associated with each node that gives me the appropriate conditional probability of each node, conditioned only on its immediate parents, right? Then how would I compute the probability of this particular assignment for those variables taking on those 5 values? And of course, the only thing I have available is the graph structure and the conditional probability tables for each one.
So you start with first probability F times probability of A times probability of S given F and A. Given F and A. And then probability of H given S and probability of N given S.
Great. Perfect. That's exactly how I do it, right? And that's because, as we talked about last time, that's the whole idea of Bayes net. It tells us how to factor the joint probability into the product of simpler probability distributions. And the reason we read off that particular set of probability distributions is those are exactly the conditional probability tables that are associated with these nodes. Right? So first we look at the probability of flu taking on the value f given its parents. Well, it has no parents, so that's not conditioned on anything. And similarly, allergy taking on the value a, it had no parents. And then sinus taking on the value s, of course, had two parents, flu and allergy, so we have to condition on what their values are, and so forth. Okay? So that's pretty straightforward. That's easy. In fact, anytime, you should hope that on the midterm, the first question is, write an expression for the joint distribution of this collection of random variables where the variables happen to be every single variable in the Bayes net, because then you'll just nail that question. That's the easiest inference question. And nicely, you can see that what's the complexity of this? Oh, it's nice. It's just linear in the number of variables in the Bayes net, because we're just multiplying together for each node in the network some number that we look up out of its conditional probability table. So we have 5 numbers to multiply together. We'll have a product which is as long as the number of nodes in our Bayes net. So it's linear in this number of nodes in the network. So that's nice. Okay. And here's a harder problem. How would we calculate what's called the marginal probability, because it only involves a subset of the variables? How would we calculate the marginal probability? That is, in this case, the probability that the variable n takes on a particular value.
Based upon s being a particular value, so multiply p of n equals little n over all the values of that. N equals little n given s equals some value over all the possible values of s.
Good. Okay. So the suggestion was, let's well, we noticed, first of all, that the conditional probability table associated with n is, what is in there? Well, that's the probability of n given s. And so one thing we could do is we could try to say, well, that equals the suggestion was that equals the probability that n takes on that value times the probability that s takes on some value summed over the possible values that s could take on, right? Oh, thank you. I wish I left a little room there. Given, yeah, let's use little s here just to, that's a little s. There. So that's certainly true. Now I detect one problem with this, which is that even though it's easy for us to read off this term from the Bayes net, because that's right here in this conditional probability table, I need a P there, don't I? We don't really know this term because we didn't store it in the Bayes net. Instead, what we have here is the probability of s given f and a. So we don't really know what the probability of s taking on these different values are unless we do some more work. Okay. So you see where this is headed. What we're going to have to do in order to figure out really what the marginal probability of s is, what we've done is we've reduced here the problem of getting the marginal probability of n taking on a particular value to instead finding the marginal probability of s. And now we're going to have to chase our way around the tree. Actually, well, now we're going to have to chase our way around the tree. So what's the general way of doing this? The general way, of course, is to go back to basics. Think of our joint probability table with one row for every possible assignment, every possible joint assignment of the variables, and say, well, the probability of n taking on the value n is just the sum over, well, let's see. We could say it's the probability. Wait a minute. I want to be careful here. I want to say it's the sum over all the values flu could take on, and allergy, and headache, and sinus, of the joint probability that flu takes on that value, allergy takes on that value, headache takes on that value, sinus takes on that value, and n takes on 1. Right? It's just the sum over all the rows in my joint distribution of all the rows for which n equals 1. And you already know how to compute the joint distribution. We just did that on the previous slide. So one way to do this is we could sum up, we could now reduce this into our factored distribution, P of F, P of A, the one we just wrote down, right? P of S given F and A, etc. And then P of n equals 1 given S. Right? But now we're going to have to sum that. We're going to have to do that over all possible configures of those variables, and that's basically equivalent to looking up all the rows in our joint distribution. Yes?
Can't we ignore the value of headache because nose and headache are two different than headache given sinus by definition?
Good point. So that graph implies that headache and nose are conditionally independent given sinus. And in this case, I think it is true that we can do this by getting rid of headache. But I'll leave that as an exercise to prove. Yes?
Since we're observing the value of sinus, does that mean it's unblocked?
Well, see, the thing is we're not observing any of those variables. That's why we have to sum over all their possible values. When I say summing over F, A, H, and S, I mean summing over all the possible 0, 1 values. So there are 16 possible. There are 16 terms in that sum. Okay? So the cost of this, what's the cost of this? Suppose we have k variables, k Boolean variables to make it simple. So the cost of doing this is what? Well, we're going to have, as we said, 2 to the 4th, 2 to the k minus 1, if we're trying to find the marginal for one of these things. We're going to have 2 to the k minus 1 terms in our sum. There's our sum right here. Right? And then for each of those, we're going to multiply together these numbers. How many of those numbers are there to multiply together? K, the number of variables. K, and let's say that's K operations, where each operation is a multiply. Right. This is a k-way multiply. K-way multiply. So we have 2 to the k minus 1 k-way multiplies that we have to do this. But it works. And it's a general formula we can use no matter what the Bayes net is. Right? We can certainly apply this technique. Of course, if it's a different Bayes net, we'll have a different factorization of joint here when we expand it out. But at least we know how to do it. And sadly, it's exponential in the number of variables in the network. which is not a big deal, really, if you have 5 variables. It's just a big deal if you have 1,000 variables. So this just is, it's going to be fine if we have a small number of variables to do this kind of brute force thing. And if you ever have to work with a BaseNet that's this size, you probably will have no trouble just doing it this way. But if you have 1,000 variables, you'll notice that it takes a long time to do the 2 to the 1,000 calculations. All right? Okay, so now we're kind of on our way. So you can see the basic idea that we're following here, the basic template we're following for doing this inference, is going back to always thinking about the joint distribution. And what the BaseNet is telling us is a simple way to factor and therefore compute any joint assignment of all the variables in the network. And so our template is for any probability expression that we're interested in, like P of n equals 1, or even P of, well, for any marginal, we could just take the fraction of rows for which that marginal is true. And in fact, for anything else, like the probability that n equals 1 and s equals 0, we can also just go through all the possible joint assignments and find out the proportion of the probability mass assigned to rows where those 2 variables take on those values. And if it's a conditional thing, then it's even easier because, of course, in the conditional expression, we don't even consider the rows in the table unless they satisfy the condition. So if we're interested in the probability that s equals 0 given that n equals 1, we only have to sum through all the rows for which n equals 1. That'll be the denominator. And then the numerator will be all the rows for which n equals 1 and s equals 0. And then that ratio will give us the probability of s equals 0 given n equals 1. OK, so we can always just kind of think that way. So the next question to consider is, what about this unfortunate intractability thing? What about the fact that this is exponential in the number of nodes in the network? What can we do? So one idea that's pretty widespread in practical uses of BaseNets is, let's do Monte Carlo simulation. In other words, if I don't want to go through all the arithmetic, why don't I just use the BaseNet to generate a random sample of values for all the variables, a random joint assignment for this according to the distribution. Okay, so what I want to do is I want to have a procedure that lets me, let's assume that I have a procedure that lets me look at a BaseNet and in time linear in the size of the network generate a random assignment of all the variables. And if I do that repeatedly, I'll get a collection of different random joint assignments that mirror the actual probability distribution, joint probability distribution. Okay? If I have that, then I can use that as a subroutine to compute pretty much anything I want to know. If I want to know, for example, what's the probability that n equals 1? Let me generate 100 of these joint assignments and just count what fraction of those 100 happen to have n equals 1. If I want to know what's the probability that n equals 1 given that s equals 0, I'll generate 100. Well, I'll keep going until I have generated 100 that happen to have s equals 0, the thing I'm conditioning on. And then I'll look at what fraction of those 100 also have n equals 1. And that'll give me the conditional probability. So you see, if I could just generate a random draw from the joint distribution represented by the network, that would be a very different way than working out all the details of the correct formula for the distribution and multiplying those terms. And this is actually an approach that many people use, especially for modest size. Well, people use it a lot. So let's see, how would we do that? How would you generate a random draw of this BaseNet? So what would you do?
Just take, randomly draw from the conditional probabilities of every node and then multiply it.
Right. So we want to somehow use these conditional probability tables. And so we could do this. What if let's start by picking the easy one, F. So first let's generate a random draw a value for F. Now, of course, the conditional probability table sitting around for F, again, assuming these are all Boolean variables, just tells us one number, which is the probability that, let's say, F equals 1. And of course, we don't have to represent the probability that F equals 0. It's just 1 minus theta sub F equals 1. Okay, so that's the thing sitting around in the table. How would we use that to generate a random draw? So we want to turn that theta into we want to give that theta to some procedure that's going to, if we call it 100 times, generate 100 random samples of F, where theta of them we expect theta sub F equals 1 of them, that fraction of the 100 random draws, to have F equals 1. So a standard way of doing that is many computer languages have a subroutine you can call that gives you a random uniform distribution between 0 and 1. So we call that subroutine. We draw a random number from 0 to 1. Let's call that R, which is in 0 to 1 uniformly. And then if R is greater than theta, let me write the other way. If R is less than theta sub F equals 1, then we output F equals 1. Right? So let's take an example. Suppose theta sub F equals 1, the probability that the BaseNet tells us that F will take on the value of 1. Suppose that's 0.9. So now what I've done is I've just said, okay, I'm going to draw a random number between 0 and 1, uniformly between 0 and 1. If that random number happens to be less than theta, 0.9, then I'm going to output F equals 1. And otherwise, F equals 0. And of course, if it's uniform distribution, this rule will give me 90% F equals 1s and 10% F equals 0s. So it's pretty easy. Okay, well, at least getting an F is easy. Now, we can do the same thing for A, allergy, because it has no parents. So what we're going to do is we're going to randomly draw a value for F. Let's call that F. So we'll draw an F and an A this way. And now we want to draw a value for S, but of course now S is conditioned on F and A. Fortunately, we already have a value for F and A. So now we just do the same kind of procedure, only we pick our theta out of the appropriate row in this conditional probability table. Right? This conditional probability table tells us how the value of S depends on F and A. We already have a value for F and A. So we just go and pick out the theta that's relevant out of the S conditional probability table. And so we draw an S given F and A. And then we draw an H given S and an N given S. And we're there. So again, we're using the factorization of the joint distribution given by the BaseNet. We come up with this one little simple idea for given a theta, how do we build a random procedure that'll give us random samples according to that theta? And then we repeatedly call that procedure with different thetas that we grab out of the conditional probability tables as we go down this directed acyclic graph. Now, aren't you glad it's acyclic? Okay. Okay, so that's how we can generate a random sample of the joint distribution. And given that, now you have a completely different general procedure for doing inference. If anybody asks you to write a program to figure out from this Bayes net what's the probability that h equals 1 and a equals 0, period, then you can just generate a whole bunch of samples and look at the fraction of those samples for which that statement is true. So in practice, this is a pretty good procedure. The one thing that can get in your way is if, for example, here's a good example of what can get in your way. It's pretty obvious. If I ask you for some conditional probability, for example, let's say the probability of f equals 0 given that a equals 1, but it happens that the thing I'm conditioning on, like a equals 1, is very rare or very low probability. So if the probability that the thing I'm conditioning on, a equals 1 in this case, is small, then I'm going to be generating all these samples, and most of them are irrelevant to figuring out the probability of something given that a equals 1, because most of the samples I'm going to draw won't have a equals 1. And so the kind of problem you get into here is those kind of conditioning on low probability events. And then this simple-minded procedure doesn't work as well. Of course, for the one that I just said, conditioning on a equals 1, it's going to be real easy because a happens to have no parents. It's one of the first things that we're putting in here. So I can just assign a equals 1. On the other hand, if instead of conditioning on a equals 1, I condition on h equals 1, ugh. You see the problem? I can't get away with doing the same thing. Because I've got this factorization tells me a way to start at the root of the DAG, possibly roots of the DAG, and go follow the arrows. Okay, so that should be, I think, clear. So the good news, and summarized here, is this idea of doing Monte Carlo sampling is very generally useful idea, because once we can sample from that joint distribution, we can calculate pretty much anything else we care about just by counting fractions of those samples. Now, if I ask what's the complexity of that, certainly to generate one sample is no big deal, right? We just had to call our uniform random generator, uniform 0, 1 random distribution procedure, k times for a k node network. And then we're just, basically that's all we're doing. So we're going to have a sample costs us a linear in the number of nodes of the network, a linear number of calls to our uniform random 0, 1 subroutine. But the question of how many samples you really need to collect to get a good estimate of the probability. You know, would you like 10 random samples to calculate the probability that n equals 1? Or would you prefer 100? Or would you prefer 1,000? Well, of course, you'd like as many as you can get. And so there's some kind of trade-off curve between how many times you generate these random samples, how big a volume of them you get, and how accurately you can estimate that thing you're trying to estimate. So these Monte Carlo methods, they only give us an estimate of these probability terms. They're not exact answers the way our first procedure was. And in fact, that's the dominant name of the game in Bayes net inference. Exact inference is NP hard. So what do we do about it? Well, either we work with a small enough network that we just don't care that it's NP-hard. That's a good solution if you have a small network. Or we hope that we have a network whose graph structure allows us to do something smarter than generating all the rows in the joint distribution. We'll see one of those in a sec. Or if we can't do that, then we resort to Monte Carlo methods often that essentially sample things. And we look at the fractions in those samples. And of course, that latter method is only give us an approximate answer to the question we're asking. There are other approaches too. You'll hear terms like variational methods and lots of other terms. And as I mentioned, that's why there's a whole course on phase nets, on graphical models. All right, so let's move on and look at one of the nice examples, which should look familiar to you if you've looked at the next homework assignment, about, here's a nice graphical model. Nice in terms of it's going to admit a nice little way of simplifying various inference questions that we have. So let's see. Let me ask you, how would I, suppose these are Boolean variables again. Suppose I ask you to compute the probability, let's say, of C equals 1. And I give you, of course, the conditional probability tables here. Okay, so, and I want an exact answer. So, of course, if I didn't want an exact answer, you could just say, well, I'll do Monte Carlo simulations. I'll generate a random sample of A, then conditioned on whatever value I pick for A, I'll generate a random sample of B, and so forth, and then I can look at the fraction of those for which C equals 1. But no, I want an exact answer. Okay, so let's start with our approach that we used before. We could say, well, it's just the sum over, I'm going to write it this way, all the values A can take on and all the values B can take on and all the values, D can take on. I'm skipping over C. Why? Because I'm asking about a particular value for C. It's just the sum over all those of the probability of A, B, 1, D, E. Right? So that's my formula for summing out all the rows in the joint distribution. Okay. And of course, given this structure of the Bayes net, we can rewrite this as what? Well, that's just P of A, P of B given A, P of, I'll say C equals 1 given B, P of D given C equals 1, P of E given D, right? So summing over all the possible values of little a, b, c, little a, b, d, and e, that'll give me the probability that C equals 1. But see, now that I've written out this factorization, did I leave out something? No, I think I'm good. So I left out something. How come I don't have? Oh yeah, this is good. Sorry. There are 5 terms there. There are 5 nodes in my Bayes net. I'm good. So now, but I see something nice going on here. Now that I've written out the factorization, I notice, for example, that this thing, if I ask what's the, before I go to the simpler way, let's ask what's the complexity of this? Well, I'm going to do 16 terms right here. Sum 16 terms, and each involves multiplying 5 numbers together, right? Okay. But now here's the simpler thing I can do. This sum, I could move over here. So I could rewrite this expression as the sum over A's and B's and D's of, and here I'm going to put all the terms that don't depend on E. Right? So what I'm doing is I'm just moving this over here because none of these other things are going to matter, right? I'm going to have, all I really have to do instead of summing together 16 of those things, I can sum together terms where I multiply just these 4 numbers together, and then I pick out the thing with the right value of D that I'm looking at. And here all I have to do is sum over the possible values of E. And so if these, for example, are Boolean variables, all I have to do is say, well, I'll do this twice. I'll do it once for D equals 0, and I'll do it once for D equals 1. And for D equals 0, I'll then just sum out the possible values of E. So when I consider D equals 1, I'll sum the probability that E equals 0 given D equals 1, and E equals 1 given that D equals 1. And so this ends up being letting me calculate a smaller number of variables. Or sorry, not a smaller number of variables, but a smaller complexity thing, because now I only have 8 terms and 4-way multiply here. Well, I guess I still have to add that in. But essentially what I'm doing is I'm eliminating the variable. In this case, eliminating E. And so it's a kind of dynamic programming thing that I'm doing. And I can do that repeatedly. Okay, so it's just a matter of rearranging, rebracketing the terms that we're working with, and noticing that we're going to be multiplying together, say, these terms involving the variable E many times, and we can just do that once and for all and store the values given that D equals 0 and given that D equals 1. And then we're good. Okay? All right, so there's the idea of variable elimination, and you'll get a chance to look more at that in the homework. Okay, so that's an example of how, if we happen to have a structure with a nice structure of our network, we can get away with some essentially dynamic programming kinds of tricks that allow us to just pre-compute sub-expressions once, store those, and then when we go, we have fewer terms that we have to add to, fewer things that we have to go through repeatedly. We just don't want to repeat sub-calculations.
That term is equal to 1.
Uh-oh. That term is equal to 1. And that's right. So this was kind of a poor example to use to illustrate variable elimination. I probably should have used the FAH, the star kind of network we were looking at. You're right. That term does sum to 1. The probability equals 0 and it equals 1 given D.
Any network, you need only to keep the ancestors of the node that you are trying to.
That's right. Because according to this network, C is conditionally independent of its, E is its descendant. Okay, I'm puzzled on this. Let me come back to it when I'm less puzzled. Let's move on. Okay, so even though my example of variable elimination seems to have this gnawing problem that probability of equals 1 and 0 given D sum to 1, obviously. There is a variable elimination method, and we'll come back to that when when I have a better example. Okay, so let's move on to looking at conditional independence again, because that's really also at the heart of understanding Bayes nets. And as we said before, one thing that's certainly true of a Bayes net is that each node is conditionally independent of its non-descendants given its immediate parents. But there are other conditional independences also implicit in the network. So while that statement is true, it doesn't get us all the conditional independences that exist in the network. And so let's push on that a little bit, and let's look at a property, let's look at a more complete rule. So it turns out we can easily state a rule. It's called deseparator. And if two nodes are deseparated in a Bayes net, then they are, if they're deseparated given some other variables, then they are conditionally independent given those variables. And we'll see what deseparation means. So how do I keep coming to that? Oh, I see. Okay, so to understand the notion of deseparation, it's defined in terms of 3 kinds of Bayes net subgraphs. And here's the first one. Now, you and I know, because we already know that, or I guess we don't. Node is conditionally independent of its non-descendants given its parents. That doesn't tell us much about this one, right? B is independent of A given C because B is independent of its non-descendants, which include A, given its immediate parent C. So that's good. We know that from our rule. Now, let's just prove that. This is another thing you should be good at. Okay, so this is another kind of mental hygiene for probability expressions kind of thing. So to say that they're conditionally independent means that we have to prove this equivalence, right? And so a way we can prove that is just to go back to the definition. Of course, by definition, the conditional probability here is just the probability of A and B and C over the probability of C, right? And now, according to this Bayes net, I can write that joint distribution. How? Well, it's the probability of A, probability of C given A, and the probability of B given C over, of course, probability of C. Okay? But now, here's the cool thing. What's that? Right? That's just the probability of A given C. That numerator could also be written as, and that box thing could also be written, therefore, as, which is, of course, the definition of that. So in other words, this equals the probability of A given C times the probability of B given C. Good. So we've proved it. So you see, what we did here, it's important to realize what we just did. We just went back to our basic definition of what the graph structure notation means in terms of how to factor the joint distribution on ABC. And then we, using that factorization, we're able to easily show that A and B are conditionally independent given C if we assume that graph structure. Okay. Here's another one. Now this one we also know. What do we know? What's conditionally independent here? Right. A and B are conditionally independent given C. And I'm not going to prove this one. I ask you to prove it at your leisure. It's easy to prove. It's just as easy to prove as the last one. You write out the joint, you get it. Okay, here's a third one. I said there were 3 substructures involved in the definition of D-separation. Here's the third one. Some people call this the collider, because A and B both have arrows colliding at C. And what can we say here? Every node is conditionally independent of its non-descendants given its immediate parents. Can't really say anything out of that statement. Can we prove this thing? Actually, no, this is false. You could try to prove it, but it's actually not entailed by that graph structure or the factorization of the joint distribution that comes from that graph structure. So, but there's something interesting that does follow from that, which is the following somewhat surprising statement. So in other words, A and B are not conditionally independent given that we know C, but the marginals are independent. They're marginally independent. In other words, if we don't know C, we can represent A and B, given no information about C, the probability of any joint assignment A-B is just the product of their individual assignments. This is a very strange thing, or it first strikes one as very strange. It's actually not. It's not even that hard to prove. Let's prove it. So this is, now again, a BaseNet defines a joint distribution over the entire collection of variables. So C is in there. It's just that we don't know its value, or we're not conditioning on its value in this case. So if we want to know what P of A and B is, and we have a joint distribution over A, B, C, then the way we want to do that is we want to sum over possible values of C of P of A, B, C. right? That's just our definition of the probability of A, B. It's just we sum out over all the variables that we're not conditioning on. And if we do that, and we rewrite this in terms of the factorization entailed here, well, that's P of A times P of B times P of C given AB. It's just that. And now again, just like I can move my sum inside, I can do it here too. So I can say, well, that's equal to P of A, P of B, sum over C of P of C given a particular A and B. And of course, that's 1. Okay, so these things really are marginally independent. It's just that if we condition on C, that independence goes away. Because the only way we get that marginal independence is leveraging off the fact that if C's got to be something, and so that term just kind of falls away. Okay, so that's what's going on. Now, if it seems counterintuitive to you, as it did to me when I first encountered this, here's an example that helps me believe it. So suppose that A and B and C are Boolean random variables that stand for whether there's an earthquake, whether there's a break-in in our house, whether there's an earthquake at our house, and whether the motion alarm in our house goes off. Okay, so now, realistically, this is a good graph to model how we think of things. We want to say the motion alarm certainly depends on if there's an earthquake or not. If there's an earthquake, it's going to set off the motion alarm. If there's a break-in, that could also set off a motion alarm. However, I don't think break-ins are any more, earthquakes are no more likely given that there's a break-in, and vice versa. So it's reasonable to say that earthquake and motion alarm are marginally independent. Knowing whether there's a break-in tells us nothing about, doesn't change the probability of there being an earthquake. But if I know that there's a motion alarm, if I know C, then all of a sudden, if I know yes or no, was there an earthquake, it changes the probability I'm going to assign to whether or not there was a break-in. Right? If I tell you C equals 1, there's a motion alarm going off in your apartment right now, and you're trying to estimate the probability of a break-in. Go ahead. Okay. Now I tell you, don't you want to know whether there's an earthquake? Of course you do. Because if there's an earthquake, that's going to explain away your hypothesis that it could have been caused by the break-in. And so some people say, well, what's going on here in these collider subnetworks is that C, once we observe it, allows us to explain away one or other of the possible things that could have caused C, things that C depends on. So that's kind of the intuition. And so if we put together these three subnetworks, we get our definition of D-separation. And this is the absolute true way to tell conditional independence statements in a Bayes net. So let's look at this definition. It says, first of all, X and Y, that's the title, X and Y are conditionally independent given Z if and only if X and Y are D-separated by Z. Okay, so now let's see, how can things be D-separated? In fact, in general, these apply to X and Y and Z don't have to be single random variables. They can actually be sets of random variables. It's even a more general notion. But we'll say X and Y are D-separated, that is, conditionally independent, given Z, if every path through the network from any variable in X to any variable in Y is blocked. Now, how do things get blocked? Well, there are two ways. A path from variable A to variable B can be blocked if it includes a node that satisfies either of these two conditions. So let's look at condition 1. The arrows on the path meet either head to tail or tail to tail, and a node which is Z. Okay, so this is like given Z. Those are two of the networks we just looked at, right? The third one says it's also blocked in the case of this head-to-head collider node if neither the node, let's call it, I'm going to call that node N. So neither the node N is in our set that we're conditioning on, nor is any of its descendants Z. Okay, so this comes back to what we just said, the explaining away the marginal independence, right? We said for this kind of collider structure, if we don't know node N, then in fact these two nodes are independent. They're marginally independent if we don't know N. What this is saying is defining not only can we not know N, should we not know N, but we shouldn't really know anything about its descendants. Because if we know its descendants, they tell us something about N. And we've ruined the assumption of lack of knowledge about N. So this second condition actually uses the collider network. And it basically says you can block the path from here to here as long as you don't know anything about this node. And that means both this thing has to be unobserved and so must all of its descendants be unobserved. Because this is not conditionally independent. Well, this is not independent of its descendants. If we know this value, that tells us something about this value, and now we've broken the, this is the alarm variable. Now we've broken the earthquake break-in mystery because our neighbor phoned us, which means probably the alarm is going off, which means now you've got a little bit of information. Okay, so this is the deseparation rule. So a path through a network is blocked if it goes through any node A, or step 1, any simple graph like this, or step 2, we have to check for these collider kind of things and make sure that the collider is not something we're conditioning on. The collider node is not something we're conditioning on, and neither is any of its descendants. So this takes a little bit of while to internalize, but once you do, it feels very intuitive. But the first time you see it, it usually takes a little grokking. So let's just look at a few examples. And this really helps. So here's the simple network. So let me ask you these simple questions. How about node x1 and x3? Are they independent given x2? Yes. Actually, let me redraw in here. If it includes the node that, so this will do it, head to tail, or tail to tail, this will do it. And then, given that we know given that we're conditioning on that one, and this one will do it if we're not conditioning on the middle one or any of its descendants. So I'll use filled in nodes to mean we're conditioning and white nodes to mean we're not conditioning. Okay, so this one's a yes. What about the next one? Is x3 independent of x1 given x2? Yes, because conditional independence is symmetric. And you just told me that x1 is independent of x3, so of course x3 is independent of x1, given the same thing. What about this one? x4 independent of x1, given x2? Yes, in fact, you could have told me that just by knowing that x2 is conditionally independent of its non-descendants, given its immediate parent. So you didn't even need d-separation. But here you can see d-separation answers the question too, because here we have, let me call this 1, 2, and 3. So this one is true by number 1, so is this. This one is true by what? What's the block? What's the thing that blocks x1 from x4? This thing, right? Because we said given x2, and x and y are d-separated by z if every path from x to y is blocked. But our definition of block meant that that z is involved. Z are the observed things. So this thing blocks it because we're conditioning on x2. Let me ask you one more. What about, well, no. Let's just move on to some other examples here. What about x3? Question?
In that last example, would x3 block even though it's not in the set?
Would x3 block even though it's not part of our conditioning? No. So the only way we can block is the node has to be in Z. And sorry, the question was, say a question again?
So would x3 block that x4 to x1 path even though it's not given? So the question is given x2, right? So x2 obviously does block it.
Oh, I see what you're saying. You're saying, you're asking, does x3 block these given that it's not in the conditioning set? Yes, thank you. Yes, it does. So this thing, x1 is blocked from x4 twice, right? Once by the observed x2, and once by the fortunately not observed x3. So thank you for pointing that out. So it's doubly blocked. Okay? Okay, so now I can ask, what about this? Is x4 independent of x1 given x3? No, because, again, this is either this or this or this collider, but now that had better not be filled in, meaning it better not be observed, and neither must any of its descendants. And that's satisfied. Oops, that's not satisfied if this is observed. So if x3 is observed, then we can't use the second case to block it. Okay, what about this one? Is x4 independent of x1 given both x3 and x2? Yes, yes, because x2 does block it by this rule up here. And we need not block every node along the path. We just need to block it somewhere along the path. Okay. And what about this one then? Is x4 independent of x1 given nothing? Yes. Because again, x3, fortunately not observed, will block it. Yes?
Can I ask a question? Like when you have the x3 and x2, like do you look at them like as one long, as the cloud or something?
Oh, when I write it this way? So let's go back to our definition of conditional independence. What we're saying is if these are conditionally independent, we're saying that the probability of x1 and x4 given x2 and x3 can be written by factoring it out as the probability of x1 given x2 and x3 times the probability of x4 given x2 and x3. So precisely that's what it means to say that those are conditionally independent. With respect to the set of variables, it means we're conditioning on their joint assignment.
My question is about the graphical interpretation. Do you look at the rules as if we kind of merge the rules and to think about them?
Do you look at the rules as?
You kind of merge the rules to
Oh, no. So the rule is stated precisely here. It says, first of all, two sets of variables, the set x and the set y. We're doing some examples where x and y are just sets of one variable to keep life simple. But in general, x, y, and z can be sets of variables. And we'll say the set x is deseparated from the set y by z, and therefore it's conditionally independent. If and only if every path from any variable to x to any variable in y is blocked. And then we can block it either of two ways, this way or this way. Both will suffice. And for any path, we need only block it at one point along the path. But if there are multiple paths, we have to block every one of them. Yes?
So for the last example, we're blocking based on the second rule on x3. However, we could say that x3 has the goal set as its descendants. So therefore, its descendants are in z. Therefore, you can't apply rule 2 to the last.
Ah, right. You're pointing out x3 has no descendants. But in this, the way we interpret this rule is that means then we don't have to worry about them being observed because it has none that are observed.
So we don't treat no descendants as the set.
Well, if it has no descendants, then we're not getting in any information about x3. And it's what we need to make x4 and x2 independent is we need that there not be any information about x3. And of course, one way to get information of x3 is to observe it. The only other way to get information is to observe some variable on which its probability depends. And since it has no such variables, then we just don't have to worry about that eventuality. Okay. All right, so let's look at a couple others just to test you out. What about this one? Is A independent of B given C? How many say yes? How many say no? Okay, the no's win. And let's see, is A independent of B given C? No, because the descendant here of node E is observed, and therefore it doesn't allow E to block this path. And of course, F doesn't block the path because even though it's one of our nice substructures, we're not conditioning on F. So again, we must have either this structure where the darkened in nodes are observed or conditioned on, part of Z, or we must have a collider structure with no information about the node housing the collision. And the problem here is that node E would have blocked it if it didn't happen to have this unfortunate descendant. But since it does and it's observed, we now know something about E, and now that no longer blocks the path. Okay? And given F, well, yes, that would do it because now we have this structure, and that'll block it. Okay? So you get the idea. It's a little bit of practice with that, and you'll really be able to just kind of look at these graphs and these conditional independencies will jump out at you. So let me just say one more thing before we end. A kind of corollary of all this conditional independence stuff we've been talking about is that if we want to know the answer to the following question, what is the Markov blanket? Or put another way, what are the nodes that we need to know in order to fully determine the probability distribution on X sub I? That's called the Markov blanket. So the Markov blanket is the set of nodes in the network such that if we know just their values and nothing else about what's going on in the network, they define as precisely as can be defined the probability distribution on X sub I. That's called the Markov blanket. And the Markov blanket is precisely the set of the nodes parents, immediate children, and co-parents. Co-parents meaning the other side of a collider that they might be pointing at. That's what the co-parent is. So co-parent other side of X sub I's colliders. It's only the immediate ones. So if we know the values of all these, we're there. Now, at first, when you see this, you might say, why do we need these co-parents? You can see that if we didn't have the co-parents, we'd still have X sub I surrounded by completely known values. And again, you have to think back to this weird intuition about colliders. If one of those descendants of X sub I, suppose X sub I is there a break-in in your apartment? Is there a break-in in your apartment? And the descendant is the alarm just went off. Then again, you're going to want to know whether there's an earthquake in order to fully, in order to precisely estimate whether there's a break-in in your apartment. So that's why the co-parents are needed. It's because if there's a collider, you've got to, you're not conditionally independent of the other parents of the collider given the collider. Then you've got to actually see those parent values too. So for that reason, this is the general structure of a Markov blanket. So if you ever see a arbitrary graphical model, which is a Bayes net, you can point at any node in that Bayes net, and you can answer the question, what's the minimum set of values of other variables you need to know in order to fully specify the probability distribution on this node, conditioned on what? And that's it. Okay? All right, so next time we'll talk about learning Bayes nets and the easy case, which you already know the answer to, learning them when you can observe all the variables, and the more interesting case, which we haven't talked about, of learning them when only some subset of the variables are observable. So that's next time.